Selecting the correct transformer kilovolt ampere or kVA rating is essential. A 12 kVA transformer is generally sufficient for the maximum load capacity of a 60 amps main breaker operating at 240 volts. However, it's important to calculate the actual kVA delivered, which is 12 kVA multiplied by 0.866, resulting in 10.4 kVA. This value should align with the panel's expected load. Other transformer options exist, but their suitability varies. A 7.5 kVA transformer is likely undersized and inadequate for the load demands of the panel. A 10 kVA transformer might be adequate but could exhibit slightly lower efficiency compared to the 12 kVA option. Conversely, a 15 kVA transformer would be oversized, leading to unnecessary expense without a proportional increase in performance. Determining the correct primary breaker size involves calculating the primary current. For a 12 kVA transformer operating with a 600 volts primary, the primary current is calculated as follows: primary current equals kVA divided by 1.73 multiplied by voltage. In this case, it's 12 kVA divided by 1.73 multiplied by 600 volts, resulting in approximately 10.99 amps. According to the National Electrical Code, or NEC, the primary breaker can be sized up to 250% of the primary current. Therefore, 250% of 10.99 amps is 27.48 amps. A 30 amps breaker is a suitable choice for the primary circuit. It provides a small buffer while remaining within the NEC prescribed limits. It's crucial to consider inrush currents which, although not always a major concern, can occur when the transformer is energized. To mitigate potential issues, consider using a transformer equipped with a slow blow fuse or other inrush current mitigation techniques on the primary side. Transformer efficiency is also an important consideration, especially at lower loads. Selecting a transformer with a high efficiency rating minimizes energy losses and improves overall system performance. In summary, a 12 kVA transformer coupled with a 30 amps primary breaker is often the most suitable choice for 100 amps, 120/240 volts panel with a 60 amps main breaker. To ensure optimal performance and reliability, it's prudent to select a transformer that incorporates inrush current mitigation measures and exhibits high efficiency. Transformers transfer electrical energy from one circuit to another through electromagnetic induction. They are fundamental components in electrical power systems, enabling voltage transformation to efficiently transmit and distribute electricity over long distances and to adapt voltage levels to suit various applications. The basic principle of transformer operation relies on Faraday's law of electromagnetic induction. A transformer consists of two or more coils of wire electrically isolated but magnetically linked. These coils are wound around a common ferromagnetic core, which enhances the magnetic flux linkage between the coils. When an alternating current, or AC, flows through the primary coil, it generates a time-varying magnetic flux in the core. This changing magnetic flux induces a voltage in the secondary coil. The ratio of the number of turns in the primary coil to the number of turns in the secondary coil determines the voltage transformation ratio. This ratio is crucial in stepping up or stepping down voltage levels. Step-up transformers have more turns in the secondary coil than in the primary coil, resulting in a higher secondary voltage. Conversely, step-down transformers have fewer turns in the secondary coil, producing a lower secondary voltage. Transformers play a vital role in power transmission and distribution. Power plants generate electricity at relatively low voltages. Step-up transformers increase the voltage to high levels, typically hundreds of thousands of volts, for efficient transmission over long distances. High voltage transmission minimizes current, thereby reducing resistive losses in the transmission lines. At substations located near urban or industrial areas, step-down transformers reduce the voltage to distribution levels, typically several thousand volts, for distribution to local areas. Further, step-down transformers, often pole-mounted or pipe-mounted, reduce the voltage to utilization levels such as 120 volts or 240 volts for use in homes and businesses. The kVA rating of a transformer indicates its apparent power capacity, which is the product of voltage and current. Selecting the appropriate kVA rating is crucial to ensure that the transformer can handle the load without overheating or experiencing voltage drops. The kVA rating should be equal to or greater than the total load connected to the transformer. Exceeding the kVA rating can lead to transformer failure. Transformer efficiency is defined as the ratio of output power to input power. Efficiency is typically expressed as a percentage. High-efficiency transformers minimize energy losses, reducing operating costs and environmental impact. Transformer losses include core losses, which are due to hysteresis and eddy currents in the core, and copper losses, which are due to the resistance of the windings. Modern transformers are designed to minimize these losses. Inrush current is a transient current that occurs when a transformer is first energized. It can be several times higher than the normal operating current. Inrush current is caused by the sudden magnetization of the core. Inrush current can cause voltage dips and can trip circuit breakers. To mitigate inrush current, transformers are often equipped with inrush current limiting devices, such as resistors or reactors. The NEC provides guidelines for the installation and protection of transformers. These guidelines cover topics such as overcurrent protection, grounding, and clearances. Adhering to the NEC ensures safe and reliable transformer operation. Overcurrent protection is essential to protect transformers from damage due to overloads or short circuits. Overcurrent protection devices, such as circuit breakers or fuses, should be sized appropriately to protect the transformer without nuisance tripping. Grounding is crucial for transformer safety. Grounding provides a path for fault current to flow back to the source, tripping the overcurrent protection device and preventing electrical shock hazards. Transformers should be grounded in accordance with the NEC. Transformer maintenance is essential to ensure long-term reliability. Regular inspection should be performed to check for leaks, overheating, and other signs of problems. Transformer oil should be tested periodically to ensure that it is free of contaminants. Transformer applications are diverse and encompass a wide range of industries and sectors. In addition to power transmission and distribution, transformers are used in electronic devices, such as computers and televisions, to provide the necessary voltage levels for different components. Transformers are also used in industrial equipment, such as motors and welders, to provide the appropriate voltage and current for these applications. In renewable energy systems, such as solar and wind power, transformers are used to step up the voltage from the renewable energy source to the grid voltage. This enables the efficient integration of renewable energy into the power grid. Special-purpose transformers are designed for specific applications, such as isolation transformers, which provide electrical isolation between circuits, and auto-transformers, which have a single winding that serves as both the primary and secondary winding. Isolation transformers are used to protect sensitive electronic equipment from noise and voltage spikes. Auto-transformers are used to adjust voltage levels in a variety of applications. Three-phase transformers are used in three-phase power systems, which are common in industrial and commercial applications. Three-phase transformers can be configured in various ways, such as delta-delta, delta-Y, and Y-Y. The choice of configuration depends on the specific application requirements. Instrument transformers are used to measure voltage and current in high-voltage power systems. Instrument transformers include current transformers, or CTs, and potential transformers, or PTs. CT are used to measure current, while PT are used to measure voltage. The secondary currents and voltages of instrument transformers are scaled down to safe levels for measurement by instruments and protective relays. Tri-type transformers are cooled by air rather than oil. Tri-type transformers are often used in indoor applications where oil-filled transformers are not permitted. Tri-type transformers are typically smaller and lighter than oil-filled transformers. The selection of a transformer for a specific application depends on several factors, including the load requirements, the voltage levels, the environmental conditions, and the safety requirement. A thorough understanding of these factors is essential to ensure that the selected transformer is suitable for the application. Consulting with a qualified electrical engineer is recommended when selecting a transformer. Electrical safety is paramount when working with transformers. Always energize the transformer before performing any maintenance or repairs. Use appropriate personal protective equipment, such as gloves and safety glasses. Follow all applicable safety codes and regulations. In addition to the aforementioned considerations, it's also crucial to consider the impedance of the transformer. Transformer impedance is the opposition to the flow of alternating current and is expressed as a percentage. It affects the voltage regulation and short-circuit current of the transformer. A lower impedance transformer will have better voltage regulation but will also have a higher short-circuit current. A higher impedance transformer will have poor voltage regulation but will have a lower short-circuit current. The choice of impedance depends on the specific application requirements. Voltage regulation is the change in secondary voltage from no load to full load, expressed as a percentage of the full load voltage. Good voltage regulation is essential to ensure that the voltage supplied to the load remains within acceptable limits. Short-circuit current is the current that flows during a short circuit. It is important to know the short-circuit current to properly size overcurrent protection devices. Harmonics are unwanted frequencies in the electrical system that can cause problems with transformers and other equipment. Transformers can generate harmonics due to non-linear loads. Harmonic filters can be used to reduce harmonics. Transformer noise can be a concern in some applications. Transformer noise is caused by the vibration of the core and windings. Noise reduction techniques can be used to reduce transformer noise. Transformer life expectancy depends on several factors, including the operating temperature, the load profile, and the maintenance practices. Proper maintenance can extend the life expectancy of a transformer. Smart transformers are equipped with sensors and communication capabilities that allow them to be monitored and controlled remotely. Smart transformers can provide valuable data about the health and performance of the transformer. This data can be used to optimize transformer operation and prevent failures. Transformer recycling is important to conserve resources and reduce environmental impact. Transformers contain valuable materials such as copper and steel that can be recycled. Regulations regarding transformer disposal vary depending on the location. It is important to follow all applicable regulations when disposing of a transformer. Transformer standards are developed by organizations such as the Institute of Electrical and Electronics Engineers, or IEE, and the International Electrotechnical Commission, or IEC. These standards provide guidelines for the design, testing, and performance of transformers. Adhering to these standards ensures that transformers meet certain minimum requirements. Transformer testing is performed to verify that the transformer meets its specifications. Testing includes tests for voltage ratio, impedance, insulation resistance, and temperature rise. Acceptance testing is performed at the factory before the transformer is shipped. Field testing is performed after the transformer is installed. Transformer failure can be caused by a variety of factors, including overloads, short circuits, insulation failure, and lightning strikes. A failed transformer must be repaired or replaced. Transformer repair involves diagnosing the problem and replacing the failed components. Transformer replacement involves removing the old transformer and installing a new transformer. Transformer upgrades can be performed to improve the performance or reliability of a transformer. Upgrades can include replacing the core, windings, or insulation. Transformer monitoring systems can be used to monitor the health and performance of a transformer. These systems can provide early warning of potential problems. Transformer diagnostics can be used to identify the cause of a transformer failure. Diagnostics can include visual inspection, electrical testing, and oil analysis. Transformer insulation is crucial for preventing short circuits and ensuring safe operation. Transformer insulation can degrade over time due to heat, moisture, and contaminants. Regular insulation testing is important to identify potential problems. Transformer oil is used to cool and insulate the transformer. Transformer oil can degrade over time due to oxidation and contamination. Regular oil testing is important to ensure that the oil is in good condition. Transformer bushings are used to connect the transformer windings to the external circuits. Transformer bushings must be properly insulated and protected from the environment. Transformer tap changers are used to adjust the voltage ratio of the transformer. Tap changers can be manual or automatic. Transformer cooling methods include air cooling, oil cooling, and water cooling. The choice of cooling method depends on the size and application of the transformer. Transformer protection devices include circuit breakers, fuses, and protective relays. These devices are used to protect the transformer from overloads, short circuits, and other faults. Transformer grounding is essential for safety. Transformer grounding provides a path for fault current to flow back to the source, tripping the overcurrent protection device and preventing electrical shock hazards. Transformer nameplates provide important information about the transformer, such as the kVA rating, voltage ratio, impedance, and winding connections. It is important to understand the information on the nameplate before working with a transformer. Transformer diagrams show the connections of the transformer windings. It is important to understand the transformer diagrams before working with a transformer. Transformer safety precautions should always be followed when working with transformers. These precautions include energizing the transformer before performing any maintenance or repairs, using appropriate personal protective equipment, and following all applicable safety codes and regulations. A 12 kVA transformer would be sufficient for the maximum load capacity of a 60 amps main breaker at 240 volts. Its rated kVA is 12 multiplied by 0.866 equals 10.4 kVA, which is close to the panel's load capacity. A 7.5 kVA transformer would be undersized and not suitable for the load. A 10 kVA transformer would be adequate but may have slightly lower efficiency than the 12 kVA option. A 15 kVA transformer would be oversized and more expensive than necessary. The rated current of the 12 kVA transformer at 600 volts primary is primary current equals kVA divided by 1.73 multiplied by voltage equals 12 kVA divided by 1.73 multiplied by 600 volts equals 10.99 amps. According to the National Electrical Code or NEC, the primary breaker can be sized up to 250% of the primary current. 250% of 10.99 amps equals 27.48 amps. A 30 amps breaker would be a suitable choice for the primary circuit as it provides a slight buffer while staying within the NEC limit. While inrush currents may not be a significant concern for this application, they can still occur during transformer energization. Consider using a transformer with a slow blow fuse or other inrush current mitigation measure on the primary side. The efficiency of transformers can vary, particularly at low loads. Choose a transformer with a high efficiency rating to minimize energy losses. Based on the information provided, a 12 kVA transformer with a 30 amps primary breaker would be the most suitable choice for the 100 amps 120/240 volts panel with a 60 amps main breaker. Consider using a transformer with inrush current mitigation measures and high efficiency for optimal performance.